All right, guys, so we're doing our final exam review to prep for those questions that you have that go back and are from units 1 through 4, dealing with kinematics and forces and energy, and then finally the concepts with waves and sound. So electricity is not on this review, that's on its separate own review, but that'll be the other part of the test as well. So in this first one, we have a motorcycle. It starts from rest and speeds up to 24 meters per second in 3.5 seconds. So I drew the dot to represent the motorcycle. It's starting at rest, and then it's speeding up, so the arrows are getting bigger. So rest, 24 meters per second, 3.5, those are all important things. So if it starts from rest, the initial velocity is 0. The speed it reaches is 24 meters per second, so that would be the final. And then 3.5 seconds is the time. So we have 3 out of the 5 in part A. It wants us to solve for the acceleration. So again, going through your old notes or old Edpuzzles, you look back and say, oh, I want the equation that doesn't have delta x in it, so the one that's missing is there. And if you use that, the proper equation would be this one. So it's Vf equals Vi plus A, the acceleration, times the time. So plugging into this, Vi is 0, so you can just ignore that. Vf is 24, so we get 24 equals A times the time, which is 3.5. You're going to solve for A by dividing through on both sides by 3.5. So that drops out over here, and 24 divided by 3.5 gets you 6.86 as our acceleration. So 6.86 meters per second squared is what you would have for that answer for part A that I just put in the box there. For part B, you're looking for how far did the motorcycle move, so that's delta x, and once you have like these, you can plug in and use any of the ones that you want. The one that I like and I think is the easiest of the equations is this one, so 1/2 Vi plus Vf times delta t. So again, just plugging in the values. We're looking for delta x, so it's already set up for us to solve. 1/2, the initial velocity was 0. The final velocity is that 24. And then it's 3.5 for the time. So if you put that in your calculator, you will get an answer of 42 meters or something close to that. So that's number 1. It's pretty straightforward, just doing kinematics. Part 2 is free fall kinematics. So instead of moving horizontally, we're vertically. So delta y switched in for delta x, and then the acceleration due to gravity, which is negative 9.8 is on Earth, is going to go in for A. So we're going to put that in. It's launched straight up from the ground at a speed of 64 meters per second. So that's our speed to start, is 64. And then it says, how long does it take to reach the apex? So how long is a time idea? And we're getting this whole chart deals with the apex. So we actually know one more piece of information. The other question B says how high it will go. So this is for part A, is the time it takes. Part B is actually asking for delta y. So we need to know something about Vf in order to have 3 items. And we know at the apex, as the object moves up into the air, it slows down. So at the highest point, it is 0. So we have 3 things, and we're going to be able to solve. So for part A, we're looking for the time. Again, part B is the one that doesn't have, part B is dealing with delta y, so we want the equation without delta y. So it's this first equation again, Vf equals Vi plus Gt. So the final velocity is 0 at the highest point. At the apex, 64 is the initial. And then it'd be negative 9.8 and delta t, which is what we're solving for. So I'm going to take this whole term to the other side and make it positive. So 9.8 delta t equals 64. And then you're going to divide through by the 9.8. So those drop out. You get delta t is close to 6.53 seconds. So again, it might be rounded slightly there, but that's close enough for us to get a good estimate, which is all these problems really do. For part B, we're looking for how high it goes. So you're looking for delta y. Again, you can use any of the equations that you like, as long as it's one that makes sense. So I'm using the 1/2 VI plus VF delta t, because again, I believe that to be the easiest one to use. No squareds or anything like that. So 1/2, the initial velocity is 64. The final velocity was 0 because at the highest point it's not moving. And then the time is the 6.53 that we just got for our answer. So you're going to put that in the calculator. And when you solve that, delta y turns out to be a really big number. It's like 209 meters. So that's a really big distance up, but it's a really high velocity to start, 64 meters per second, so it's going to go far. All right, so that's the first two. The third one is our first Newton's law and free body diagram kind of net force situation, and we did this in person. So it says a 75 kilogram person, so that's our mass, rides an elevator standing on a bathroom scale from the first to second floor. As the elevator begins to move up, its acceleration is 2.3 meters per second squared. Between the floors, the elevator is at a constant speed. And then as it reaches the second floor, the elevator slows down and the scale reads 600. So we're supposed to draw free body diagrams for these. So let me just start out by kind of thinking about what are the forces acting on our object. So if we're the person and we're the object, we have gravity, the force of gravity pulling down. And you should note that the force of gravity for all of these should be the same size, because the gravity is not changing. The Earth is pulling on that person with the same amount of pull each time. So even though these arrows might be slightly different in size, they should be all equal. And if we wanted to figure that out, we'll do that later. We'll do m times g. So it would be like 75 times 9.8. So we'll get that for our weight. And let me just give you that number. So that's 735. So we have 735 newtons trying to pull down. Now, in order for the, in the first part where it's accelerating upward, in order for it to accelerate upward, the force up has to be larger than the gravity force. So I'm going to call this the normal force. It's the reading on the scale. It's the same thing. When they're moving at a constant speed, that means the velocity is constant, so the acceleration is equal to 0. And if the acceleration is equal to 0, that means these have to balance. So this normal force in this part is going to be equal. That normal force and the gravity force are going to be equal. And then to slow down, the normal force would have to be less than the gravity force, because you are moving up, but you want it to slow down, so the force going down has to be bigger. And then we're going to use kind of these tables, or you could use the equations to try to figure out these ideas. So in each of these cases, we have the normal force, which is positive, and the gravity force, which is negative. So we said that for all of these gravities, it's negative 735. And then the net force is equal to m times a. So for this first part, we're looking for the reading or the scale, which is the normal force, as it's pushing up. We know the acceleration is 2.3, so it would be 75 times 2.3. That's m times a, so that's going to get us our net force here. And when I did that, let me put that in the calculator. So 75 times 2.3 is 172.5. So basically we're trying to fill in this box here. So some number minus 735 gets you 172.5. So if you add those two numbers together, you make that positive. And you add the 735 to the 172.5. For this one, the normal force, or the scale reading, is 907.5. So that is how much force the scale is pushing up on the person to make them accelerate at that rate. So that's the first one. For the second one, we already kind of talked through that these have to be balanced. So if it's balanced, the acceleration is 0. So if you put a 0 in here, it'd be 75 times 0, which is just going to get you 0 for the net force. So the net force is 0 here. We still got normal force and gravity. So this is negative 735. So some number that we're trying to figure out plus negative 735 gets you 0. So this is just going to be a positive 735. So the normal force is completely balancing out the gravity force at that point when it's moving at a constant velocity. Finally, it says that the normal force reads 600 in the problem when it's slowing down. So this normal force is a positive 600. We still have a negative 735 because that's our constant gravity going down, Fg. And then when I add those together, I would get a negative 135. We're looking for the acceleration, so F net is equal to ma. So negative 135 equals 75a. And you're going to divide through by 75 on both sides to get a. And that acceleration is equal to negative 1.8 meters per second squared. So we did that in the lab a long time ago, but it's really the same idea. It's just kind of doing the free body diagrams, looking at them, setting up the chart, adding together to get the net force, which is F equals ma, using gravity equation Fg equals mg to do that kind of work and solve for whatever's missing. We have a different situation in this one. So number 4, it reads a person pushes a 17 kilogram, which is the mass, box at a constant speed. Constant speed again means the velocity equals 0. So our velocity isn't 0, it's constant. So the acceleration is 0. So it's moving at a constant speed. 30 Newton force going to the right. So I'm just going to label this the push. And it's 30 going to the right. So this would be positive 30. And it's not pushing up or down, so that would be 0. It's on a level surface that has friction. So there's friction acting here. And if it's moving at a constant, this and that, those friction force and that pushing force are going to have to be balanced. The other forces that are acting, we got gravity, and then the normal force. And they are also going to balance in the vertical direction because the constant speed is 0, so the net force is 0. So if I go through all the forces, I got gravity, I got the normal force, I got the friction. We're adding all that to the push, and we're going to get the net force. So again, based on our picture, we just labeled the forces. Now we're going to do the directions of those forces. So we did positive 30 and 0 for the push. The gravity is not going in the x, it's going downward in the y, so that's negative. The normal force is going nothing in the x and positive in the y. And then finally, the friction force is negative in the x and 0 in the y. It's got an acceleration of 0, so that means that this x direction 0, also the y direction almost always balances out and makes it go to 0. So we're just looking for a couple boxes. So 30 plus some negative number gets you 0, so that's going to be a negative 30 for the friction. So that one's pretty straightforward. So just adding these down to get to 0. For gravity, the equation is m times g. So it'd be 17 times 9.8. If I do 17 times 9.8, I got a value of something like 166.6. And then that's going down, then we need the same thing going up. So it needs to 166.6 going up. So those are all the forces, their sizes and directions, they're all listed there. The coefficient of friction is u. So we're looking for the u value. And that's from the fun equation. So FF for the friction is the coefficient times the normal force. So we're just going to take these numbers and plug them in. So 30 is on the left side, u is what we're looking for, and then 166.6 is on the right. You divide through by the 166.6 on both sides to get u. So the coefficient turns out to be, I rounded this a little bit, but it's like 0.18, so that's really close. It's like 0.18000 something, but that's the coefficient of kinetic friction, which is describing how slippery the surfaces are that are going together. All right, the next one, only a couple more. The next one is a roller coaster problem. So there's a roller coaster up here, starting at the top of the hill. It's going through down a hill, up around a loop, and then it's finishing up at some level, which is not quite at 0. So part A, it wants to know what's the total energy of the coaster at the beginning of the ride. It says it's at rest and it's at a height. So if it's at rest, that means the velocity is 0. So there's no kinetic energy at the initial point, but there is a height. So the total energy at A or initially, is equal to just the gravitational potential energy. No springs, no rubber bands, anything like that. So that's the gravitational potential energy initial. So it's just going to be mgh, which would be 1,000. Sorry, I'm shoving this in. So that's the mass. 9.8 is gravity. And then the height is 22. So when you put that in your calculator, it should give you a big number. It's 215,600 joules. So that's the answer to part A. Part B wants to know, okay, at a point later in the ride, the coaster is completing a loop at a height of 12 meters. So this is point B here. So it's in the loop, and it's got to be moving through the loop. So it's got a velocity there. I'm going to know how fast the coaster is moving. So we're just going to use conservation of energy. So the total initial energy that we had should be equal to the total energy at point B and at every other point. And we already know this number on the left side. So 215,600 joules is the initial. On the right side, we got two different types of energies here. So we got gravitational potential energy and kinetic potential energy, or kinetic energy, not kinetic potential. But that's where the velocity is. So we're going to figure out how much gravitational potential energy it has there from mgh. So m again is 1,000 because the mass of the roller coaster hasn't changed. Little g is 9.8. And then the height here, this loop is not as high as where it started, so it's only 12 meters instead of 22 meters off the ground. And then we have, for kinetic, the mass, which is 1,000. And then that's v squared. So we're looking for v, and you can plug all these numbers in your equation. But when I do 1,000 times 9.8 times 12,000, or some times 12, so let me just do that. 1,000 times 9.8 times 12. I got 1,17600, and we're going to subtract that from both sides. So if we do that, the 215,600 minus 117,600, you get 98,000. So 98,000 is equal to 500 v squared. And then again, it's just doing the algebra to solve for v. So divide through by 500. And then you're going to take a square root. So when you divide by 500, that's 196. And then when you take a square root, you're going to get v is equal to 14 meters per second. So that is how fast that coaster car is moving at that moment when it's at the top of the loop there. Part C asks you for if the cart comes to rest at a final height of 5 meters, so this is now 5 meters, we want to know how much work was done to stop the car. So it comes to rest, so the velocity is 0. So obviously, if you compare the energy here and the energy here in terms of just GPE, there's a drop in GPE, and the amount of work would have to make up for the difference in those two. So again, conservation of energy, the total energy initial, which is what it started out with, that's this 215,600 number, should be equal to the total energy at the very end. And again, it's just kind of breaking it up into parts. So 215,600 is the initial. On the right side, we have gravitational potential energy, so it's still 1,000, 9.8. And this time the height is 5, so we're going to put in a 5 here. Sorry if that's a little sloppy, but you can hopefully understand it when I read it. And then whatever the difference in that is going to be the work. So the work by the external forces to change the energy. So if you put in 5,000 times 9.8, you get 4,900, or 49,000, excuse me, and then you subtract 49,000. That's 3 zeros from that. And then you get the work is 166,600 joules. So 166,660. Oh no, I put in an extra 6. That's a 0 too. Sorry. 166,600. That is the answer to part C. Okay. One more energy one just to practice some energy stuff. So it says a child and a sled have a mass of 65 kilograms. They start from a height of 6 meters. It reaches a speed of 7 meters per second at the bottom of the hill. We want to know the GPE at the top. So this is pretty similar, again, to what we just did. So the GPE at point A would be the mass times the gravity times the height when it's at height of A. So the mass was 65. We're going to multiply that by 9.8. And then we're going to multiply it by the height, which is 6. So if you do that, I got 3,822. So that's the gravitational potential energy to start. Part B, it says when it's at the bottom of the hill, it's moving at 7. So we want to figure out how much kinetic energy it has there. So kinetic energy at B would be 1/2 mv squared when it's going at point B. So if we plug into that, it's 1/2, the mass is 65, and then that velocity would be 7 squared. This is a smaller number. You only get 1,592.5 for that. So that's joules still. So the energy is different, right? So the difference in those energies would be the other form of energy that would be present. So it says how much energy was changed into heat and sound. So if you're doing conservation of energy, so the gravitational potential energy at the A position should equal the kinetic energy at the B position. And if they're not equal, then you have some other work or non-mechanical energy. We called it non-mechanical energy in this one. So you're just going to take the difference in those two numbers and get the answer. So 3,822 is on the left side. That's equal to 1,592.5 for the kinetic energy that we just got the answer to in B. And then we're solving for the heat, sound, the non-mechanical energy. So you're going to subtract the 1,592.5 from both sides. And you'll get the non-mechanical energy here. And that's equal to 2,229.5 joules. So that's how much heat and sound energy was present in order to make that sled slow down. So that was only going 7 meters per second at the bottom. All right. Last question is a graphing one. So you have a wave shown to the right in this picture. So it says displacement as a function of time. It wants to measure the amplitude. So the amplitude, again, is the height of the wave. So if I go up here, it's in meters. So the amplitude A would be 1 meter. You could also look at it, the amplitude from here to the bottom. So that this is just a negative amplitude. That would be a positive amplitude. Okay. It asks what's the period. Period is the amount of time that it takes for one cycle. So again, you just measure from crest to crest or trough to trough. Crest to crest here, this looks like it's about 1.5 and this looks like it's 8. So just estimating that out. So that's 1.5 seconds, that's 8 seconds. So the difference in those two would be a period. So 8 minus 1.5 is 6.5 seconds. So 6.5 seconds is the period of oscillation. For frequency, frequency is just 1 over the period. So you're going to take the inverse of the 6.5. So 1 divided by 6.5. And if you do that, you'll get like 0.154, and that would be hertz. Moving down here because I don't have a lot of room up here. So the speed of a wave is given. And we're asked to solve the wavelength. So again, wavelength is lambda, it's this symbol. So I got 58.5 equals 0.154, because that was our frequency calculation we just got, and then lambda. So you're going to divide by 0.154, doing the algebra here. So those drop out, and lambda turns out to be 380 meters or so. So it's a pretty long wave. Okay, so that's that answer. That's part D. Finally, the type of wave, I would call this a crest, and this is a trough, and this is another crest. So crests and troughs go with transverse waves. So that's our picture of a transverse wave here because of the pieces that make it up. So I would call this transverse. All right. So that is it. That's the whole review. Transverse. There we go. That's the whole review sheet. Hopefully you feel pretty comfortable with those ideas. Again, you're going to have some choice. So there will be 4 kind of problems from the first 4 units, 1 from each, and you just have to select 2 of those. So pick whichever ones you feel most comfortable with, do those, and then hopefully that'll turn out well. So again, best of luck. Thank you for doing a great job this semester, and be well.